Okay, good afternoon or evening or morning, depending on where you are. Uh, Today is our ninth day. Yesterday we did uh, um, what's what was it? Yeah, cone problems, and we did some practice on them. So you had a work period day. Today we move into the next kind of related rate, uh, and this is the distance problems, which are basically right triangles, so Pythagorean theorem with the squares in them and things like that is what we're going to be doing. So we're going to be looking at those today. And I'm going to do three different examples of these. As you can see, I got the first one up here. But the one thing that you have to remember is if a distance, with the distance related rates, you could have a positive or negative rate now. Okay, you could have a rate that is shrinking, which is considered a negative rate if the rate between the is getting smaller, then it's negative. If it's getting bigger or growing, we call it a positive rate. Okay, because if you're approaching each other like this, like if you're running towards each other like this, you have a negative rate. If you're driving away from each other, you have a positive rate. Okay, so that's what this first point means here. Okay, so moving away from each other is a positive rate, approaching each other is a negative rate. Okay, so that's something that's important when we use related rates. Now we're going to be using related rates that come up with a right triangle in them. Okay, so we've done cones and we've done spheres. Now we're going to do right triangles. Okay, and I've got three different examples that we're going to go through here. If I'm going too fast, just pause and get down the question here. So for my first example, it's an example, a vertical elevator type example, and we're going to be looking at the hypotenuse here. So it says Kelly is in a glass elevator on the outside of a building, which is climbing at a rate of 3 meters a second. Her friend is standing on a sidewalk 24 meters away from the building base. Find how fast the distance between the two is increasing at a point when the elevator is 45 meters off the ground. Okay, so the first step that we do with these is we draw our picture out. So I'm going to use a straight line tool because we're going to get a right triangle here. So if this is my ground here, and this is a building right here, okay, and then that elevator's at 45 meters there, and then her friend is down here. We have this is the hypotenuse is the distance between them. I'll label all this, of course. So this is my ground. Okay, and so let's say, well, that's not a terribly accurate one, is it? Because this is 45 and this is 24, so this should be smaller. Let me draw it a little better here. I'll just undo a few of these here, and I'll draw it in a little bit better. Okay, so it's 45 meters high and 24, so that bottom one should be shorter like this. Should make it a little more accurate in our drawing there. Okay, so there's a better representation. Okay, so let's get our marker out here and put in our knowns. So okay, so step one is to draw it. Sketch and define your knowns. Okay, so here we have the building, and here we have the elevator, and then her friend is here. I don't know why I have her standing on her head. Okay, so friend is there, and we're looking at that point on the ground. And we know that this is 24 meters away from the base. And then this is 45 meters here. So let's define some variables. Let's call this horizontal distance x, this vertical distance y, and this hypotenuse distance z. So x, y, and z. So the relationship between x, y, and z, so y is the vertical distance, x is the horizontal, and z is the hypotenuse distance. Okay, so that's our diagram there. So now it's telling you that how fast is the distance between the two increasing. So we know that, first of all, that she is going up at a rate. Kelly's going up. The elevator is going up at a rate of 3 meters a second. So we'll call that dy dt equals 3 meters a second. Okay. Now, this rate here where her friend is she moving at all? No, she is not moving. So the person on the x-axis is not moving. So we know that dx dt, she is not moving towards the building or away from the building. If she was, there would be a rate given. But because she is standing put, we know that she's moving at 0. And what we're trying to find out is, what is the distance that's changing between the two, which is this distance here. This is she's moving here. How much is this growing? If this one's growing, and it is growing because if she started here and went up, it's getting farther and farther away. She's getting farther and farther away, so that's why this is positive. If she was coming down, this would be shrinking. This would be negative, but she's going up. It says climbing at a rate. Okay, so this is our unknown. So our second step is to now relate the triangle formula between x, y, and z. So step 2, use the equation. So we know that x squared plus y squared equals z squared. So the first thing we have to do is we know what x is and we know what y is. So if y is at a particular time, we have to find out what z is at the moment in question. So find z with the moment in question, which is when the elevator is 45 meters above the ground. Okay, so this is 45, this is 24. What's z going to be? So we have to figure that out first. So 24 squared plus 45 squared equals z squared. So that will give us our moment for z. It's not a 2, that's a z. Okay, so take our calculators out and get that particular moment. Okay, so sometimes we just call it finding the missing side. Get my calculator, 24 squared plus 45 squared. That's 22,601. So z equals, if we take the root of that, we get 51. Okay, so now we've found find Z with the moment in question. So we can say find the missing side, because it might not only be Z sometimes. Sometimes it might be one of the other two. Okay. Step 3 now is to do differentials of the equation. Take the derivative of the equation to add in the rates of change. Remember, the rates of change were here. dy dt was 3 because the elevator is going up 3. dx dt was 0 because she's not moving. This person is not moving on the ground. And dz dt is what we're trying to find out. So we're going to relate those three together. So we're going to, step 3, take the derivative. Okay, so our derivative is, okay, we've got 3 variables here, but we have 2 given differentials, so that's fine. And we're going to find the third. So the derivative of this is 2x dx dt plus 2y dx dt, or dy dt, pardon me, equals 2z dz dt. Okay, and then we can reduce the differential equation. 2 can come out of all of them. So x dx dt plus y dy dt. Oh, not 2 y's in there. Equals z dz dt. And now we plug our numbers and solve for dz in the last step. Okay, so in our case, we've got x was 45 meters times 0 meters a second, rate of change for the person on the ground, plus 4, or that wasn't 45, pardon me, that was 24, correct? Was on the ground, yes, 24, if we look back at our diagram. X was 24, Y was 45. My mistake. So this should actually be 24 meters here. It's going to cancel out anyway. And then this one would be, Y was the 45 meters. And her rate of change for Y was 3 meters a second. And that's going to equal our Z, which was 51 meters times dz dt. Okay, because we had 51 was what we calculated as at that particular moment in time. Okay, so this is 0 plus 45 times 3, that's 135 meters squared seconds equals 51 meter dz dt. Okay, and then we're going to divide that 135 meters squared seconds squared by 51 here to get 2.65 meters per second. And it's growing because it's positive. And that is the distance in which they are growing apart from each other along that hypotenuse. Okay. All right, so that's our first example. Let's move into our second example. I'm intending to do 3 today. So we kind of did that one. So now we're just follow the same steps. So I did it where this wasn't changing. The next one I want to do, they're both going to be changing. Okay, and maybe we'll have one in there that's negative as well. So let's pop this over to the next one. Say a car is approaching an intersection, and it says approaching an intersection, traveling east at 60 kilometers an hour. A truck is moving away from the same intersection, traveling south at 50 kilometers an hour. How is the distance between the two vehicles changing at the moment the car is 21 meters from the intersection and the truck is 20 meters from the intersection? So you might think you might have to change all the units in here, but as long as you use the same units and you watch your canceling, you probably don't need to in this case. So let's draw out our particular case here. Okay, so we've got the car coming in traveling east. Okay, the truck is moving away from the intersection, so away from here, and traveling south. Okay, it's a little bit slow. What is it, 21 meters and 20 meters, so they're about the same. And we're interested in this hypotenuse here. Okay, so at the particular stuff that we know, if we label everything up, just like we did in the first one, this is our car, this is our truck. So dc dt, okay, if you think about the car in here, it's approaching the intersection. So this line is going to get smaller as the car comes towards the intersection. So that's going to be a negative 60 kilometers an hour. Okay, so it's shrinking its distance. The truck, we'll use a capital T. Okay, it's going away, so it's lengthening its line out. So that's going to be a positive. Okay, now our instant in time I'm going to put inside. So dz dt is what we're trying to find. In instant in time, the car at how for the distance between the two vehicles changing. The car is 21 meters away, and the truck is 20 meters away. So let's figure out what z is. So we go. We'll call this one x, this one y, and this one z. I guess we should probably keep it with the t and the c's so I don't confuse you guys. We'll call this one c and this one t. So c squared plus t squared equals z squared. Okay, so we got 21 meters plus 20 meters equals z. Okay, so let's get a calculator out, figure that out. 20 squared plus 21 squared, that's 841. Okay, square root that, what do we get? 29. So this is 29 as we, in that instant in time. So now we're going to use the equation to calculate this. So we know that c squared plus t squared equals z squared. So this would be 2c dc dt plus 2t dt dt equals 2z dz dt. Now we can cancel out those 2's, okay? Because they're all the same on both sides. So that means we're left with our equation. So C was 21 meters. This is where, and her car rate was negative 60 kilometers an hour. And then we added our truck, which was 20 meters, times our truck rate, which was positive 50 kilometers an hour. And that's going to give us our Z, which was 29 meters, times a dz dt. And dz dt will be in kilometers an hour if we do all of this. So this is our equation to solve. We go 21 times 60 negative, and we get negative 1,260 meter kilometers per hour, plus 1,000 meter kilometers per hour equals 29 meter dz dt. Okay, so we're going to get a negative number of negative 260 meter kilometers per hour. And then over on this side, we're going to get 29 meters dz dt. So now when we divide out 29 on both sides, the meters will cancel out. To get our answer. Okay, so we go, okay, so we have 260 negative divided by 29. So that means negative 8.97, we'll say. So we got 8.97 negative kilometers per hour. That means they are approaching each other. Because they are negative, meaning they're shortening their distance. Okay, and there's a situation using that example. So we'll do one more. Okay, we'll do the practice stuff tomorrow because I want to do so far we've done an example that had a hypotenuse changing, and then we did another example with a hypotenuse changing. First one we had a constant, non-changing. One of the distances weren't changing. Second example, we did the two legs were changing. Now we're going to do an example where the hypotenuse changes and you have to find one of the other distances. Type example, and this will be our final one for today. Okay, so let's see here. This one here I think we'll use. Okay, so let's pop this one up. Okay, so this is one where the hypotenuse is going to be, and I'll draw it out here. I didn't draw it out yet, but I'll draw it out for you. It says a man on a dock is pulling a boat by means of a rope attached to the bow of the boat 1 meter above the water and passing through a pulley located 8 meters above the water. Okay, so the difference between that is 7, right? If he pulls the rope at a rate of 2 meters per second, how fast is the boat approaching the dock when the bow of the boat is 25 meters from the point 7 meters directly below the pulley? So let's draw this out so that we can see it better. Okay, so here's our water. And then up here is our pulley. Then here we go. This is a right angle. So here's our pulley, and he's pulling down on this at a rate, and we'll call this one Y. We'll call this one Z, and we'll call this one X. So we want dx dt. We want to find the rate at which the bow is approaching the boat. We don't know that. Now he's pulling down here at a rate of 2 meters a second. Okay, so you have to think about this one a little bit. First thing we're going to do is let's get all these things. So if the bow is 1 meter above the water and this pulley is 8 meters, so this is 7 meters. And then it says at a point when the boat is 25 meters from this point right here. So this is a right angle, by the way. So this is 25 here. Okay, and then we'll figure out what these two rates are here, but let's figure that out. It's 2 meters, he's pulling here. So this means that his dz dt that he's pulling here, if you think about it, it's 2 meters a second, but which way is it going to be getting shorter or is it going to be getting longer? Well, it should be getting shorter. So dz dt equals negative 2 meters a second. Now, what about dy dt? Okay, if you think about dy dt, the pulley is fixed there. Is this pulley moving? Is it a movable pulley? No, so this is like it's fixed there. So because it's fixed, y is not changing. So the rate, this length of y is never going to change. It's always going to be that 7 meters above the boat bow. So that's 0 meters a second. Okay, so now we're going to be calculating this dx dt instead. Okay, so there's our diagram. Let's get our instant and time to find z. So we know that x squared plus y squared equals z squared. So our x was 7, or pardon me, was 25, and our y was 7. So this is 25 plus 7. Okay, so let's do that. So 25 squared plus 7 squared. That gives us 674 equals z squared. If we take the root of 674, what do we get? We get 20. Push the wrong button there. Let me do that again. Square root, I did cube root for some reason. 674. 25.96. Okay, so it's 25.96. We could probably just round it off to 26, but I'll just leave it there. We'll just do that, and we'll do the rounding at the end. So now once we've got those instances, and we know that that's 0 and that's negative 2, we got to find this one. So we got to do the relation between x squared plus y squared equals z squared. So that's again 2x dx dt plus 2y dy dt equals 2z dz dt, and we can cancel those 2's out. And now we plug our results in. Okay, so let's get this. X was 25 meters dx dt, that's what we're trying to find, plus y, which was 7 meters times 0, equals z, which was 25.96 meters times negative 2 meters per second. Okay, so if we do that, we're going to get 25 meter dx dt's equals times 2. So we get negative 51.92. meter squared per second, and then we divide it both sides by 25 meter. To get our dx dt equaling, and what do we get there when we divide by 25? I get 2.08 negative meters per second. So that means it's approaching the dock at 2 meters a second. Okay, so that takes us about 30, almost 31 minutes. That's long enough. So tomorrow, there's a lot of distance questions. I'm going to modify them a little bit. This year, I'm going to make them not have so many. There's too many there. So I'll cut it down a little bit, and there'll be some practice distance questions for you to work on tomorrow, and I'll post the solutions up as well. So tomorrow will be a work period on these distance type problems. And then we get into our last little bit with related rates, and that's something that's related to physics, and that's distance, velocity, and acceleration, how they're related to each other with derivatives. Okay, so we'll stop there today. Best of luck with your practice tomorrow.